All right, let's work on a couple more examples. So the next example has to do with a balloon that's being inflated. So let's say air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. The question is to find the rate of change of the radius when the radius is 2 feet. Find the rate of change of the radius when the radius is 2 feet. First of all, notice that the problems are getting actually shorter in the type of information that we are receiving. Well, for this particular problem, we could try to draw an image. You have a balloon, right? And you may have a pump. Say the pump looks like this. Yeah, I didn't. Definitely not gonna win any awards with my drawings. Let's say you're filling that balloon with air, right? So you're inflating it. Now, as air is being pumped into that balloon, that air is coming in at a rate of 4.5 cubic feet per minute, which means that the volume of the balloon is changing. As the air comes in, the volume of the balloon increases. The more air you put in, the bigger the balloon gets. So let's let let's let V be the volume of the balloon, and R be the radius. Well, we know that the volume is increasing at a rate of 4.5 cubic feet per minute. So we know the volume is increasing at a rate, and this rate is constant, of 4.5 cubic feet per minute. Okay, now we know that at time t, the rate of change of the volume dv dt is 4.5 feet. And I'm going to write this as a fraction. It's 9/2. So 9/2 is equal to 4.5. So this is the given information. So given is dv dt is equal to 9/2. And we want to find the rate of change of the radius. So we were asked to find the rate of change of the radius when the radius is 2 feet. So we want to find dr dt, because that's what represents the rate of change of the radius, when the radius is 2 feet. Now, again, the most difficult part of this problem, once we have identified our given and our missing information, is to find something that relates the two variables. So I have radius and I have volume, and I have a sphere. Well, turns out that there is indeed an equation that relates the volume of a sphere to the radius of the sphere. So volume of a sphere, if you remember from 8th grade math, which I don't suspect that you do, it's 4/3 pi r cubed. So here we have clearly related the volume with the radius, because the volume is equal to the radius cubed times pi times 4/3. Now, much like we did in the previous examples, we will take the derivative implicitly with respect to t on both sides of the equation. So we have dv dt, the derivative of v is dv dt, and that is equal to 4/3. Remember, this is the constant multiple rule, so 4/3 is a constant, pi is a constant, so they stay the same. But now we have the derivative of r cubed. I'll do it on the side so you can see it. R cubed, its derivative is going to be equal to 3r squared, but because we're taking this derivative with respect to t, we're using the chain rule, so we're going to multiply that by dr dt. So we have 4/3 times pi times 3r squared times dr dt. And the reason why I'm writing it in this way is so you could see that the 3's are going to cancel here, because I have 3 divided by 1/3 or multiplied by 1/3. So they're going to cancel out. So we have dv dt is equal to 4 pi r squared dr dt. Again, 3 divided by 3 is 1. Okay, so now we have an expression that expresses the rate of change of the volume in terms of r squared, or the radius times the rate of change of the radius. But we are actually not trying to find the volume. We know what the dVdt is equal to. We know that that's going to be equal to 4.5 cubic feet per second or per minute. But what we're actually trying to find, we're trying to find dr dt. So we have to solve for dr dt here. Now notice that we are multiplying dr dt by 4 pi r squared. So the opposite of multiplying by 4 pi r squared is to divide both sides by 4 pi r squared. When we do this, assuming obviously that r, so long as r is not equal to 0, which is not, because we have a sphere which is increasing in size, but anyway, we will cancel this side, so we have dr dt on the right side is equal to, and the way that I'm going to write this, I'm going to write it as, because it's a bit cleaner, I'm going to write it as 1/4 pi r squared times dv dt. The reason why I'm writing it like this is because we're going to be substituting into it in a second. Yeah. Okay, so let's actually do our substitutions. We know, so recall from above, dv dt, we were given that to be 9/2 cubic feet per minute. And we know that r, we were told to find r at when r equals 2, when r was equal to 2 feet. So we simply plug in now into the function that we just developed, which is 1/4 pi r squared times dv dt. Well, if we plug in the values for r and dv dt, we get 1/4 pi times 2 squared times 9/2. Well, what is this equal to? This is equal to 2 times 2 is 4, and then 4 times 4 times 4 is 16. So we have 16 pi times 9/2. And you could do the multiplication. If you multiply across, you get 9/32 pi. This is the RDT. And if you use a calculator and you round to the nearest hundredth, you get that this is approximately equal to 0.09 feet per minute. Okay, so one thing to notice here is that the volume was increasing at a constant rate. We were told that the volume was increasing at a rate of 4.5 cubic feet per minute, whereas the radius is actually not increasing at a constant rate. The radius is increasing at a rate that varies. and it varies based on the radius. Yeah, it varies in with respect to the radius. In this particular case, notice that the radius is growing more and more as the volume, not as the volume, as the time increases. So the bigger the time, the bigger the radius, because the more inflated that the balloon will be. Okay. Let's do another one. This one is a little bit more challenging. We have an airplane that is flying on a flight path that will take it directly over a radar tracking station. Now, we're told that if S is decreasing at a rate of 400 miles per hour, when S is 10 miles, what is the speed of the plane? So what we have here, we have an airplane we have an airplane that is traveling at some speed, right? And this airplane eventually is going to reach a radar tower, right? It eventually is going to reach some radar tower. Now, this particular radar tower is at, let's see, oh yeah, I forgot to give you this information. One more piece of information is missing. So let me append this. There's a piece of information that I neglected to write. The plane is flying at an altitude 6 miles from the station. It's flying at an altitude of 6 miles and S miles from the station. So here S is the miles. Good. So what I mean by that is the following. This plane is at a height of 6 miles. So that means that when it reaches the station here, when it's right above it, it's still going to be up 6 miles. And now the distance from S, so the distance S from the station is not actually this horizontal distance, because this horizontal distance is towards this point here. The station is down here. The distance to the station is denoted by S, which is this line right here. Okay, this is the horizontal distance X. We'll call it X because we don't know what it is. Right, so all we know is that the altitude is 6 miles, and we know that S is decreasing at a rate of 400 miles per hour. And we're told that when S is 10 miles, what is the speed of the plane? So we're looking for the speed of the plane when S is 10 miles. So now we are saying that X here, that X that I drew up here, is the horizontal distance from the station. And this assuming, of course, that the station would have been lifted up to 6 miles in the sky. If we use the Pythagorean theorem, we could actually find out what S is. So remember, the Pythagorean theorem says c squared equals a squared plus b squared. So that relates the hypotenuse of this right triangle with this adjacent side of x and this adjacent side of 6. And when I say adjacent, I mean to the 90-degree angle. So if S is the hypotenuse, then that means we have 6 squared plus x squared by the Pythagorean theorem. And we actually could find out what the value of S here will be. We could actually find out what this is. If we take the square root on both sides, we have S is equal to plus or minus 6 squared plus x squared. Now, I'm not worrying about the plus or minus because this is in relationship to distance. So distance is always positive, so we pick the positive distance. That means that S is equal to 36 plus x squared. Right? Yeah, 36 plus s squared. Now, this is the value of S. Now, here I was told that S is equal to 10. So if S is equal to 10, in fact, I could have done it up here. But if S is equal to 10, actually, yeah, let me do it up there. If S is equal to 10, we have 10 squared, I'm using this one right here, equals to 36 plus x squared. This will give us the value of x. And why am I interested in the value of x? Because I need to figure out what this distance is up here to actually be able to complete the problem. Because I'm looking for the speed of the plane, so I need that distance to find it. So I have 100 equals 36 plus x squared. If we subtract 36 from both sides, we have that 64 is equal to x squared, and then if you take the square root on both sides, we have 8 equals x. So now I'm almost done with this triangle. You know, we have x equals 8, and I know that s is equal to 10 because that was given to me. Okay, so I was given that s was equal to 10. Now it's always important that once you have a shape or relationship, like if you had a rectangle and you're only given one side, let's say x equals 2, then it's important that you always find the other side before you begin taking derivatives and whatnot. That's why I decided to find out what x was. Since I already know that I have a 6 and that I have a 10, you might as well find out what the other side is. And again, you could do that by using the Pythagorean theorem, since we're dealing with a right triangle. Well, I also have now a formula that relates all three variables. I have the actual Pythagorean theorem itself, which I have up here. But before we begin to take derivatives again, let's summarize the information that we have. So we know that x is equal to 8. We know that we're looking for s when s is equal to 10. And we know that the height is 6 miles. Okay? I'm not even going to bother to write it because it's just a constant. That's not changing. The altitude of the plane is staying constant throughout, so we don't have to worry about it. We do know what the SDT is. That was given to us. That was the decrease. So we know that S is decreasing at a rate of 400 miles per hour. Now this is where reading is important. If S is decreasing at a rate of 400 miles per hour, that means that the SDT is equal to negative 400, because the negative here will indicate that we are decreasing. And remember, S is the actual distance of the plane to the station. It's the hypotenuse in this triangle. Okay, so that's what's decreasing at a rate of 400 feet per second. And what we want to find, is the speed of the airplane, and the speed of the airplane is actually given by dx dt, which is the reason why I decided to go and figure out what x was, because I'm gonna need it. Okay, so from above we have s squared equals to 6 squared plus x squared. That's from, again, this formula right here, the Pythagorean theorem. We could now take the derivative implicitly on both sides with respect to t. So we will have 2s times ds dt being equal to, remember the derivative of a constant is just 0, so that goes away. And the derivative of x squared is going to be 2x times dx dt. Now, what are we solving for? We are solving for dx dt. We're solving for this. So that means that I'm going to divide both sides by 2x. So if I divide both sides by 2x, again, so long as x is not equal to 0, we could cancel this out. We have that dx dt is equal to, and the 2's cancel out here, so this is equal to s over x times ds dt. And guess what? We have values for s, x, and ds dt. And this is why I decided to find the x value above there to save us this work now in the end. Because we will not be able in this class to figure out the solution to this problem without knowing all of the unknowns. Okay, so what do we have here? S was equal to 10, x was equal to 8, and ds dt was equal to negative 400. And that was equal to dx dt. You could choose to multiply the 10 times the 400. If you do that, that will be negative 4,000 divided by 8 equals dx dt. And then 40 divided by 8 is 5, so this is going to be equal to 500, negative 500 dx dt. Now, keep in mind, we were looking for the speed of the airplane. So we're looking for, let's see. Yeah, we're looking for the speed of the airplane. So we have that the speed of the airplane is 500 miles per hour. Okay. Now, you may say, yeah, there's a negative in there, but remember, speed is also a positive value. The negative just indicates the distance that is decreasing between the airplane and the station. So we have that the speed of the airplane is 500 miles per hour. Okay. All right. So here again, the most difficult part of the problem is understanding what you're dealing with, meaning understanding the relationship between all of the variables involved. In this case, they were related by the Pythagorean theorem. And as such, it is important that once you have the relationship and you have a picture of what you're dealing with, that you figure out the values for each variable that you're given, because they're all gonna play a role in the end. Right here, you can see that all of the variables play a role: s, x, ds, dt, and dx, dt. Mind you, somebody could have given you the velocity. So one way that if we were in person in classes, the way that I will change this problem up, if I was to give you this as a quiz, is I will actually give you the speed of the airplane as being negative 500 miles per hour, and then I will just ask you, what is the rate of change of the airplane in relationship to the tower? So in that case, you will actually be looking for ds dt. That's a perfectly valid question to ask you with the same parameters. Okay. All right, so let's do our final example. So our final example will involve something similar. Let's see. we have a television camera, for example, television camera at ground level is filming the liftoff of a space shuttle that is rising vertically according to the position equation which is given to us as S equals 50 t squared, where S is measuring feet and t is measuring seconds. Then we're told that the camera is 2,000 feet from the launch pad. Now the question is, find the rate of change in the angle of elevation of the camera at 10 seconds after liftoff. Okay, so right now we only have one actual number to work with, which is at seconds after liftoff. So that is corresponding to time. Before we begin, again, trying to figure out what we're dealing with, it's always good to draw an image. So what do we have here? We have a rocket or a space shuttle, kind of like this, right? And the space shuttle is some distance above the ground. So, we have the tower here, right, where it's shooting up. And then we have a TV camera, right? We have a TV camera that's recording this situation. And the angle of elevation that we're talking about is like when you raise your head. If you raise your head, like when you're at the movie theater, most people don't like sitting in the first row because your neck is going to hurt by the time that the movie ends because you have to elevate your head a lot. Whereas as you move back to the later rows, you can actually bring your head down, the angle of your elevation of your head down, so that you are almost parallel with the screen. So here, what's happening is the opposite of that movie theater example. So we have the distance between the camera and the rocket, at least at the ground, being 2,000 feet. That was given in the problem. Right here. Then we know what the elevation of the rocket is. So we know that the rocket is going up, right? And it's going up by S. So we are told that the rocket is rising vertically according to the position. This is supposed to be position, not posizione. Position equation S. And we're told what S is equal to. S is equal to 50t squared. So this is in relationship to S. And the angle of elevation is this angle theta that we open up here. And that angle theta is Just assume that this is a straight line. It doesn't look too good. Let me redo it. This particular angle theta is what we're interested in finding out the rate of change of. It's better. Okay, so we have this triangle figure to work with. So again, the camera is 2,000 feet from the base of the launch pad. The rocket is going up by a distance of s, and s is equal to 50 t squared. And we are interested in finding the rate of change in the angle of elevation of the camera. And I just said that the angle itself is theta at any given time t. So again, let me write all that down. Let theta be the angle of elevation. Okay, angle of elevation. Now, we are given some information. We know we want to find the rate of change when 10 seconds have passed by. 10 seconds after liftoff. Well, that means that t is equal to 10. And when t is equal to 10, we know that the height of the rocket is s equals 50 times 10 squared because of this formula. That gives us the height of the rocket, 50t squared. And we know that t is equal to 10, so we have 50, 10 times 10 is 100, so 50 times 100, which equals 5,000 feet. So after 10 seconds from liftoff, we know that the height of the rocket is equal to 5,000 feet. Now, we know that we want to find the rate of change of the angle of elevation. Remember, the rate of change is always going to be given by the derivative of the variable with respect to time. So the derivative of theta with respect to time t is d theta dt. So that's what we want to find. And we want to find this, again, when t equals 10 seconds after liftoff. And since we already calculated what happens with the position of the rocket, we know that when t equals 10 seconds, by the work we did up here, the position of the rocket is 5,000 feet in the air. Now, notice that we have s here, and we have d theta dt. What is the rate of change of the position of the rocket? That is something very important that we need to find out. What is the rate of change of the position of the rocket as time passes by? Because we know that that's changing as the rocket keeps on rising. Well, we find it again by taking the derivative. To find the rate of change of s, meaning ds dt, we have to take the derivative on both sides. So we have ds dt is equal to, well, the derivative of 50t squared is 100t. Notice I did not write let's say dt because that's just one. Like if you were to write it, you could think of it as being an actual variable. It would just be one. So we don't actually write it because we're taking the derivative with respect to t. So it's redundant. There's no needed. Anyway, that is 100t. So now we know that ds dt is equal to 100t. So I think that now we have almost all the information that we need to actually solve this problem. Now, again, what do we want to find? We want to find the rate of change in the angle of elevation. We now need to actually find out how the angle is related to the elevation. Again, how the angle is related to the elevation. In the previous example that we had with the airplane, we're looking at the speed in relationship to the change as we move closer to the tower, which is a little bit different. We did not care about any angles in this particular problem. Here, this is completely different. So how is this angle theta related to that side S? Well, now is a good time to remind you of something that you should definitely know from at least 7th grade, and that is SOHCAHTOA. Remember SOHCAHTOA? SOHCAHTOA tells you that sine theta is equal to opposite over hypotenuse, and cosine theta is equal to adjacent over hypotenuse, and tangent theta is equal to opposite over adjacent. Well, here, for this angle theta, I do have two pieces of information. I have S, which happens to be the angle opposite, and I have 2,000 feet, which happens to be the side adjacent to the angle theta. I don't actually have the hypotenuse. I actually don't have the hypotenuse, but I do have the side opposite and I have the side adjacent. So if I have the side opposite and I have the side adjacent, that means that I'm working with tangent. Okay, so now I know that the angle theta can be related by the equation tangent of theta being equal to, again, opposite over adjacent. Well, what is the opposite side? Opposite side is S, and the adjacent side is 2,000. So we have tangent theta is equal to S over 2,000. So now I know how my variables are related. I know how my angle theta is related to the height of the rocket. Okay? What can we do now? Well, now we are actually ready to take the derivative. So if I take the derivative with respect to t on both sides, I have that the derivative of tangent of theta, remember the derivative of tangent is secant squared theta, and because I took the derivative with respect to t, we have d theta dt being multiplied by secant squared. And then on the right side, don't worry too much about the 1 over 2,000 because that's just a constant. So by the constant multiple rule, we only need to worry about the derivative of s. But the derivative of s with respect to t is just 1 times ds dt. So we just left with ds dt. Okay? Remember, what are we looking for? We are looking for d theta dt. That's what we want to find, d theta dt. So right here we have d theta dt times secant squared theta. So what I can do is I could divide both sides by secant squared theta. Instead of dividing both sides by secant squared theta, I'm going to do something which essentially is the same thing. I'm going to multiply both sides by 1 over secant squared theta. So I multiply both sides by 1 over secant squared theta. It's the same thing as dividing by secant squared theta. So now we have some cancellation. This cancels with this. So we get d theta dt is equal to 1 over 2,000 times ds dt times 1 over secant squared theta. However, now we have to be a little bit clever. What is secant? Secant of theta, so recall, secant of theta is equal to 1 over cosine of theta. So if I have 1 over secant of theta, what I really have is 1 over cosine of theta. But you could work this out, 1 over 1 divided by 1 over cosine of theta is the same thing as 1 times cosine of theta by the keep change rule method, so we simply get cosine of theta, right? So this is 1 over secant of theta. So 1 over secant square of theta is actually the same thing because we could pull out this square sign. So we have d theta dt is equal to 1 over 2000 times ds dt times 1 over secant of theta squared. I'm allowed to do that. But now we actually saw what 1 over secant of theta is. Secant of theta is simply cosine of theta, and cosine of theta squared is simply cosine squared theta. So we have here now is the following expression. So we have 1 over 2000 times ds dt times cosine squared theta. Trust me, we're almost done with this problem. We know what ds dt is, so we could substitute it in. We found ds dt all the way up here. ds dt is equal to 100t. So I'm going to substitute it in right here. So what we have is d theta dt is equal to, I'm going to put the cosine in front, cosine squared theta, times 100t divided by 2000. Yeah, just 2000. Now, what is cosine squared theta? What is cosine squared theta? Well, if we look back at our picture, we can actually figure out now by using the Pythagorean theorem what the hypotenuse is. So we have to figure out real quick what the hypotenuse is. So let's do that on the side. I'll do it on the side here. And the reason why I'm doing that is because I know by SOHCAHTOA cosine is adjacent over hypotenuse, and I already know what the adjacent side is. Adjacent is 2000 feet. So if I could find the hypotenuse, then I could find out what cosine squared of theta is, that angle theta. So again, by our triangle, we have 2000 and we have s. And we're looking for x. So that means that x squared is equal to s squared plus 2000 squared. That's by the Pythagorean theorem. So that means that x is equal to the square root of s squared plus 2000 squared. So that is actually what the hypotenuse is by the Pythagorean theorem. This is the square root of s squared plus 2000 squared. But now I know what cosine is, because cosine is adjacent over hypotenuse. And the adjacent side is 2000 and the hypotenuse is the square root of s squared plus 2000 squared. So we have d theta dt is equal to, and remember this is squared, so I could pull it out. It's going to be equal to 2000, that's the adjacent side, divided by the hypotenuse, which is s squared plus 2000 squared, the whole thing squared because of the square on the cosine, times 100t divided by 2000. Okay, so now we're almost done. Believe you me, we're almost done, because now we have everything in terms of t's and s's, and we know what t is. T is 10. That's from the problem. We want to find out what the change in the angle is after 10 seconds, and we know what s is. S is the position of the rocket at 10 seconds, and we found that somewhere down here it was 5,000 feet. So we simply plug in 10 and 5,000 and we will get our solutions. So let's do that substitution. The theta dt is equal to 2000 squared. And again, when s is 5,000, we're going to have 5,000 squared plus 2,000 squared. We're going to take the square root of that times 100 times 10 divided by 2,000. Okay? So let's see what's happening here. So we have d theta dt is equal to, I'm going to move the square to the inside. So it's going to be 2,000 squared up here. And then the square is going to cancel out the square root down there. So we're going to have 5,000 squared plus 2,000 squared times, well, 100 times 10, that's 1,000, divided by 2,000. Now, students in college algebra class will immediately, say, oh, this is 1/2. But we're in calculus, so we know that we don't want to simply do this right away. We actually notice that we have a 2,000 on the top and a 2,000 on the bottom, so we could cancel one of them with the other. So we're going to be left in the top with 2,000 times 1,000 divided by 5,000 squared plus 2,000 squared. Now, to make a long story short, you could use now a calculator to figure this out. But after some cancellation, if you square 2,000 and square 5,000, you add them and then you multiply 1,000 by 2,000. This is going to actually be equal to, after you simplify, 2/29, and this is in radians per second. So this means that the rate of change for the angle theta is equal to 2/29 radians per second. So when t equals 10, meaning the time is 10, theta is changing at a rate of 2/29 radians per second. This was a long problem, but it's a very good problem, because notice how many times we had to actually rewrite our equations. We were not given the height as being constant. The height was changing. It was variable. It was in terms of a variable. It was varying with respect to time. Not only that, but we also had multiple relationships with not only the angle, but we also the sides. We ended up having to find all three sides of this triangle at 10 seconds. In order to actually take the derivative, we ended up having to use the fact that we could relate the angle theta to the side opposite by tangent. Then we took the derivative implicitly on both sides. And then after some cleverness with cosine, we ended up also rewriting cosine of theta, and then we substituted. And after the substitution and the simplification, we get that the rate of change of the angle theta with respect to time t at 10 seconds is 2/29 radians per second. This concludes this lecture on related rates. Related rates, it's not an easy concept. It's probably one of the two most difficult parts of Calculus 1 for students. So if you got lost along the way, I don't blame you, but I suggest coming to office hours or attending tutoring. Thank you for your time.